Hello students, today we will continue with the second module in partial differentials and multivariable calculus as part of the course CHE 614 Mathematical Methods in Chemical Engineering at IIT Kanpur. Just as a way of very brief recap of the previous module, in the previous module we introduced the notion of what is called a total differential, which is a very important idea in partial differentials or multivariable calculus. So if you have a function of two variables f of x and y, then if you want to find out what is the change incurred in the function f due to infinitesimal changes in the variables x and y, then we will obtain this infinitesimal change in f, which is called the total differential df, as partial f partial x at constant y dx plus partial f partial y at constant x dy. Okay, this is one of the fundamental ideas in partial differentials or multivariable calculus. Now, as I told you in the last lecture, this can be generalized if instead of function of two variables, if you have a function of n variables, f of x1, x2, so on up to xn, again df is nothing but partial f partial x1 dx1 partial f partial x2 dx2 plus so on plus partial f partial xn dxn. The key thing about these partial differential is what is kept constant. Here all the xi's except x1 are constants. Here all the xi's except x2 are constant, and so on. And here all the xi's except xn, they are constants. Okay, so this is the basic idea of total differential. Now in the last lecture, the last module, we also talked in some detail about what is the meaning of the partial differential, and the importance of understanding what is kept constant in a partial differential is very important. If you simply write partial f partial x, and if f is a function of many variables x, y, z and so on, okay, if you simply say partial f partial x, this does not make any sense because we have not clearly specified what is kept constant. Okay, so this part is not clear. So unless we say this, then this partial differential will not make any sense. So this is one very basic thing that's kind of obvious when you understand what is the basic idea behind partial differentials, but yet this can lead to source of confusion if you don't understand this properly. Okay, now let's understand, or let's discuss one very important application of the idea of a total differential. Okay, so suppose you have a function of n variables. Let's say f is f of x1, x2, so on up to xn. So as I just told you, the total differential is nothing but partial f partial x1 dx1 plus partial f partial x2 dx2 plus so on plus partial f partial xn dxn. And I have already told you what is kept constant here, so I'm not going to repeat it for the sake of brevity. Now in some cases it can happen that these variables x1, x2, so on up to xn, they are not independent. That is, they are linked or they are related by some equation or a constraint. Okay, so there are additional equations. For example, let's assume that x2, x3, x4, so on up to xn, they are all some functions of x1. So effectively, if you use all these relations where x2 is written as a function of x1, x3 is written as a function of x1, and so on, let's call this 2. Okay, so now then effectively f becomes a function only of x1, right? Because you can eliminate all the other variables and in favor of x1, and you can write f essentially as a function of x1. But if you were to let me just take a new sheet. If you were to know this relation, but it is cumbersome for you to explicitly write f as a function of x1, you can still find the total differential df, okay, in the same way as partial f partial x1 dx1 plus partial f partial x2 dx2 plus so on partial f partial xn dxn, right? Now if you take the total differential of df with respect to dx1, this will give you partial f with respect to partial x1, and dx1 by dx1 is 0, and you'll get partial f by partial x2 by partial x1. I'm sorry, dx2 by dx1. There is no need for partials here, so let me write it as plus so on up to partial f partial xn dxn by dx1. Because we know that all these other variables x2 x3 so on up to xn are related, we have assumed that they are all related to x1, we can find their changes with respect to x1. So this is called the total derivative of f with respect to x1. Whereas this object, the first object that I have drawn here, is a partial derivative, right? We all know that this is a partial derivative of f with respect to x1. So this is the change that is incurred by f, not because of keeping all the other variables constant and varying x1, because of varying all the other variables as well, but because all the other variables are also linked to x1, you have to account for these changes. Now this notion of a total derivative is very useful in fluid mechanics and transport phenomena, in what is called in coming up with this notion of what is called a substantial derivative, okay? So, or let's just write this name, okay? The same idea in fluid mechanics and transport phenomena goes by the name of substantial derivative. So what does it mean? Suppose I say that temperature is a function, temperature in a fluid is a function of x, y, z and time, where x, y, z are nothing but just give me one. Okay, so this is x, y and z. This is the coordinate axis and t is time. Okay, so this is a fixed reference frame or a Cartesian reference frame about which you are trying to analyze the problem. Now temperature is told as a function of x, y, z at various points in space, and also as a function of time if needed. Now often we are interested not in looking at the variation of, suppose I take a given point and ask what is the variation of temperature at this point. Let's color it slightly differently. Okay, let's say this is a point we are interested in. If I ask the question, how does the temperature change as a function of time at this point, then that information is given by the usual partial derivative of temperature with respect to time, because here I am keeping x, y, z constant, that is partial temperature upon partial time by keeping x, y, z constant. Okay, this is the partial derivative of temperature with time, which gives you the local variation of temperature with time. Now often in fluid mechanics and heat transfer, especially involving fluids, right, you have a given material, given point in flow of fluid, which is marked in red here, and you would like to measure the rate of change of temperature as you follow that particular point as a function of time. Now, that time derivative is called the substantial derivative of temperature with time, and it is given a special symbol called capital D temperature upon D time. Okay, so this is a very important notion in transport phenomena. This is called the substantial derivative. What is substantial derivative again? It is the derivative that you obtain by following the motion of a given given fluid particle, let's say here, and then as it travels from here to here, then you are interested in telling or finding out what is the rate of temperature, change in temperature as a function of time as you follow the particle. Now, what is kept constant in this time derivative? It is also a time derivative. What is kept constant? Now, following a particle means, following a fluid particle means labeling a particle in terms of its initial positions, capital X, Y, Z. Suppose I have a particle at time t equal to 0, its locations are capital X, Y, Z, and then as time changes, this particle moves elsewhere, and the same particle at a later time t, after time t, it occupies the current location X, Y, Z. So here what we are trying to say is that the current location of the particles are functions of the initial location and time. Y is function of X, Y, Z and time. Let's call it Fx, Fy, and Z is function of X, Y, Z and time. Okay. Now, the substantial derivative is nothing but the time derivative, the partial derivative of temperature with respect to time, let's say in this example, by keeping capital X, capital Y, capital Z constant. This is the definition of substantial derivative. Okay. Now, how do we get, the idea is to relate this to partial t, where x, small y, small z are kept constant. How do we do this? Let's take a one-dimensional example. By one-dimensional example, I mean that there is variation only in the x direction. We ignore y and z directions for the moment. Okay, we can generalize this immediately after we understand this simple example. Now, if temperature is a function of x and t, then the total differential of temperature is partial temperature by partial time at constant x dt plus partial temperature by partial x at constant time dx. Okay, this is something that we just learnt from our previous module on partial differentials, right? Let me take a new page. Okay, so now x is a function of the initial position of the particle capital X and time. Notice that I'm ignoring the y and z coordinates. I'm assuming things are varying only along the x direction. So dx is partial x by partial capital X, okay, at constant time dx plus partial x by partial time constant capital X dt. So we also had dt as partial t, partial time, constant x dt plus partial t, partial time at constant, partial x at constant time dx. Now I'm going to substitute for dx here in this expression from the previous expression. Okay, so if I do that, it's a very straightforward algebraic operation. So I'll get the total differential of temperature is partial t, partial temperature, partial time at constant x dt plus Now I'll write this partial derivative as such. Now instead of dx, I'm going to assume, I'm going to write partial x by partial x constant t dx plus partial x by partial t at constant x dt. Okay. Now the next thing is, we know that the substantial derivative or the total derivative of temperature with time is the partial derivative while keeping capital X constant in this 1D example. So what I will do is, I'll take this expression for dt and differentiate with respect to time, keeping capital X constant. So this is, if I do from the right side, okay, now dt by dt is 1, so the first term will simply give you partial t by partial x at constant capital X. Now if I look at this term, remember I'm keeping capital X constant. That means that if I keep capital X constant, that means that dx is 0 if x is constant, right? So this term will not contribute. So what I will get therefore is simply partial t partial x constant t, and from the second term here I'll get partial x partial t at constant capital X times dt you have already differentiated. Okay. Now therefore the substantial derivative dt by dt, which is nothing but the partial derivative of temperature with time keeping capital X constant, is the partial derivative of temperature with time keeping small x constant plus the partial derivative of temperature with respect to x at constant time times dx dt at constant x. Now let's look at this particular term in a little bit detail to understand what this means. So here we are looking at a given fluid particle which is moving as time progresses. Okay, its current position is given by x. Now if I follow the same particle, its position x is changing as a function of time, and if I look at the rate of change of position of that particle, this will give me the velocity of the fluid particle. So I can rewrite this expression as dt by dt is nothing but partial temperature partial time at constant x, plus instead of this I'm going to write v sub x. The x denotes the x component of the velocity, plus, okay, so this expression is called the substantial derivative of temperature. Okay, and this comes directly as a consequence of this comes directly as a consequence of the basics of multivariable calculus. Substantial derivative, sometimes it's called the total derivative. If you look at a little bit of continuum mechanics literature, they will call it the material derivative, and so on. They all mean the same essentially. Okay. Now I can also generalize this to 3 dimensions. So I've illustrated this for the sake of simplicity in 1 dimension. So the substantial derivative in 3 dimensions is given by partial t partial time at constants x, y, z plus vx partial t partial x plus vy partial t partial y plus vz partial t partial z. Okay, so let me write this more carefully. Okay, vz. Now this can also be written as partial t partial time at x, y, z plus, if you know a little bit of vector calculus, this is nothing but v dot grad t. Okay, so let me box this for you. Again, this is called the substantial, sorry about this, this is called the substantial derivative. Okay, now this is called the local time variation at a fixed point in space. This is called the convected time variation, because while the fluid is flowing, it can move from regions of higher temperature to lower temperature, vice versa, and that also results in the change in temperature of a given material particle. Okay, that is the convected rate of change. Okay, now let's go to, I hope this is clear to all of you. This is a very fundamental idea in all of fluid mechanics and transport phenomena, and this comes directly as a consequence of multivariable calculus. Okay, now I'm going to discuss very briefly the notion of another very important topic, the notion of exact and inexact differentials. This is of great importance in thermodynamics, so I'll spend a few minutes on this. Now, so far, what we have been discussing is, suppose I give you f, then how to find df, right? If I say f is a function of x, y, then you now know that df is partial f, partial x, constant y dx, plus partial f, partial y at constant x dy. This is something that we have discussed frequently, right, so far. Now, what if I ask the reverse question? What is the reverse question? Given df, given an expression for df, can we find f? That's the question I'm asking. Okay, for example, if df is written as x dy plus y dx, okay, then if I consider f, if I somehow guess f as xy plus some constant c is a constant, then you can immediately verify that df is x dy plus y dx. Okay, such differentials of many variables which integrate directly to give the function, they are called exact differentials. Okay, they are called exact differentials. Now, if I consider another example, let's consider x dy plus 3y dx. Okay, now suppose if somebody is giving me this expression, now question is, can we find the function from which this differential could have come, this total differential could have come? Now, if I integrate this partially with respect to x keeping y constant, let's integrate this partially with respect to y keeping x constant. If x is kept constant, dx is 0. So I'll get xy plus some constant. This is obtained by partial integration with y, meaning when I say partial differential integration, it is keeping x constant. Don't vary x. Similarly, if I do the converse, keeping y constant and integrating with respect to x, I will get 3xy plus some constant c2. This is partial integration with x keeping y is equal to constant. Okay, so regardless of, and when I have to mention one very important point which I just didn't mention. If I partially integrate this with respect to y, then the constant can in general be a function of x. Likewise, if I partially integrate this with respect to x, the constant can in general be a function of y. Now, regardless of what you choose these values for constants, whether they is function of x or constant or 0 or whatever you choose, you will never have these two to be the same. That means that this is not consistent. So this is an example of an inexact differential, because it doesn't directly integrate to give you a well-defined function. So one can ask the question, what are the properties of a differential that makes it exact? Okay, so in general, if I consider df of a of xy dx plus b of xy dy, right? If this had come, if I argue that if df is obtained from a function f of xy, then that function, the total derivative of that function is partial f partial x dx plus partial f partial y dy. Now, if I were to compare the two, then I will say that this corresponds to a of xy by comparing these two equations. This corresponds to b of xy. Now, if the function is well behaved, I told you that the mixed derivatives are the same. So, I know that partial squared f by partial y partial x is partial squared f by partial x partial y, which implies that partial a by partial y should be equal to partial b by partial x. Okay. Now, it turns out that this condition is a necessary and sufficient condition for a function to be, for this differential to be exact. So, if I have a differential of the form, okay, which I have shown here, if I have a differential of the form here, then in order for it to be exact, then you have to, the differential has to satisfy this condition. That is, the two differentials, the two coefficients of the infinitesimal variations dx and dy should satisfy this. Now, if I were to quickly tell you what happened to that simple example that we took, okay, the example we took was x dy plus 3y dx. Okay, here a of xy is equal to x, b of xy is equal to 3y. So, partial a by partial y, oh, I'm sorry, a of a is the coefficient of let me just, so let's rewrite this a little carefully, because the way I had written it, I had first written the differential dx and then dy. So let me rewrite this a little slightly differently. Okay, so what we have is 3y dx. The first term is the coefficient of dx, and then the second term is the coefficient of dy. If we were to do this, then this becomes a of xy and this becomes b of xy. So partial a by partial y becomes 3 and partial b by partial x becomes 1, and these are obviously not equal. That means that this is an inexact differential. Okay, so this is a very, very important concept in thermodynamics, because you know that there are two types of functions. One are called path functions, like work, heat, and there are state functions, which are like internal energy and entropy and so on. So path functions are inexact differentials, state functions are exact differentials. Okay, you will learn the consequences of these in thermodynamics, but for now all you have to understand is just this, that you can figure out whether a differential is a partial differential expression is exact or inexact by this simple identity. Now, there are a couple of useful theorems or useful results. Let me say they may not be exalted to the level of theorems. These are often used in thermodynamics, but not just thermodynamics, maybe many other areas as well. If z is a function of xy, then I can convert this or equivalently represent this as x is a function. I can invert this around or turn this around and write like this. And similarly, this can be turned around to write this as y as a function of x and z and so on. Okay. Now consider x is a function of x is x of y z. Then dx is partial x partial y at constant z dy plus partial x partial z at constant y dz. Okay. Now, because y is a function of xz, I can write the total derivative, or sorry, the total differential of y as partial y by partial x constant z dx plus partial y by partial z constant x, not dy, I'm sorry, it should be dz. Okay, now look at this expression. You have dy here, and this can be substituted back in here, and what you will get, if I just substitute and rearrange terms, I'll get dx is equal to partial x partial y at constant z partial y by partial x constant z dx plus partial x partial y at constant z partial y partial z at constant x plus partial x partial z at constant y dz. This is just rearranging terms after substituting dy from this expression to this expression here, and collecting terms. There's nothing more that I've done, so you can try this yourself. It's fairly straightforward. Okay, now there are two results on one that one can get. Suppose I take x as constant. Okay, if I take x as constant, then dx is 0, that you all know. If dx is 0, then this is 0, this is 0. That means partial x partial y at constant z. That means this term, which is the coefficient of dz, must be 0. So plus partial x partial z at constant y is 0. Or if I take this to the other side, partial x partial y at constant z partial y partial z at constant x is minus partial x partial z at constant y. Okay, instead, if I consider let me take let me generate some space here. Looks like I have to go to the, okay, let me do one thing. Let me copy this whole thing to the next sheet. It'll be easy for us. Just bear with me for a minute. Suppose let me just select rectangle. Okay, I think I should be able to do this. Yeah, sorry about the delay. I'm just getting used to this new gadget that I have. Okay, okay, now suppose I consider, let me use a different color for this. Suppose I consider z is constant, that is dz is 0 in this expression, then this entire term will become 0. So dx cancels, so I'll get partial x partial y at constant z times partial y partial x at constant z is 1, which implies that partial x partial y at constant z is 1 over partial y partial x at constant z. Okay, now if I look at this expression, I can rewrite this as minus 1 over, using this relation, a similar relation rather. This is minus 1 over partial z partial x at constant y. I can just flip these variables. Instead of y and x, I can put z and x, and then y becomes constant, and so on. And so what I'll essentially end up getting is partial x partial y at constant z partial y partial z at constant x is minus 1 over partial z partial x at constant y. If I take this to the other side, this gives partial x by partial y constant z partial y by partial z constant x partial z by partial x at constant y is minus 1. This is again very frequently used in thermodynamic manipulations that many of you may be familiar. Still, I thought I would generalize this or derive this very interesting and important result so that you are comfortable with this when you encounter this in other subjects. Okay, So what I will do is I will stop this module here for now. In the next module, what I will do is to complete the discussion on partial derivatives and multivariable calculus. Okay, so until then, goodbye.